Hey, once again, afternoon, folks. This time around, I'm going to close limiting equilibrium by a similar problem to the first one that I did. We might see that there's a pattern that we are repeating. When an object is on an inclined plane, there is tendency that it might either slide up the plane or down the plane, depending on a comparison of the weight component and the driving force or the upward or pulling force. Um, when that happens, remember, friction is always a force opposing motion. So if the tendency of the object is to slide down the plane, then friction will be facing up the slope. Or if it goes in reverse fashion where the tensional force or the pulling force has got a higher magnitude as compared to the weight, it means the tendency of the object is to go up the plane. Hence, when we have such type of problems, we might be interested in looking at what we call the least or greatest possible value. Think the points I'm talking about are highlighted there. So let's have a look at the picture that we see. This is an object on an inclined plane. So our interest, I've got a feeling, is centered around P. But remember what we said last time, that weight is a force that's always uh, pulling the object towards the center of F, and we get it by multiplying mass by uh, acceleration due to gravity, which we call g. So weight will be 0.6 multiplied by 10. So our weight is going to be 6 newtons here. But remember, because it's on an inclined plane, it will now bring components. The angle is still the same 21 degrees, but we are going to have a perpendicular component here, which is going to be of magnitude weight cos theta. So that's weight is 6 cos the angle highlighted there, 21 degrees. Then going this way, we have a component parallel to the slope, which is the weight component. This time around, I'm going to enlist it here, where I'm saying it's 6 sine of 21 degrees. So we've got a driving force, we've got an opposing force, which is the weight. So depending on the direction that the object is about to move, it will determine where our frictional force will be inclined towards. But now, if we want to make this interesting as a quiz, when friction and P are facing the same direction, in other words, if we have our friction facing upwards, it means the weight of the object is bigger than the force P. Hence, it's going to give us a least value of P. Well, but if friction turns the other way around, when the object is about to go up, it means we'll get the greatest value of P. So let's check. The information is saying a particle of mass 0.6 kilograms is placed on a rough plane which is inclined at an angle 21 degrees to the horizontal. The particle is kept in equilibrium by a force of magnitude P newtons acting parallel to a line of greatest slope of the plane, as shown in the diagram. The coefficient of friction between the particle and the plane. So we are given the value of mu, so it means we can easily find friction. Show that the least possible value of P is 0.47, correct to 3 significant figures, and also need to find greatest possible value of P. So let's try and navigate this problem. Remember, perpendicular to the plane in an upward direction, we have our normal reaction force. Um, then downwards, we're having our weights. These problems are nice because whatever calculation we do, if we reach 0.47, it means our calculations will be accurate. So let's try and check. This object is stationary because it's experiencing equilibrium, though it's about to move. I'm sure that information is there, that there we are keeping it in equilibrium. So there's a balance between the driving force and the opposing force. So for this scenario, if we want P to be least, it means it's going to be P plus friction there equal to the weight component, which is pulling the object downwards, the 6 sine 21 degrees. But remember, F is calculated as mu R. If you want friction, you need a product of mu and R. Well, with mu, we are okay, we have it below there. But with R is going to be equal to the perpendicular component of weight. So R is equal to 6 cos 21 degrees, because we assume this object is not bouncing. So when that happens, let me scroll up a bit. We'll then have to substitute to say P plus mu. Mu we said is 0.3. So that's 0.3 multiplied by 6 cos 21 degrees. We are saying this is equal to 6 sine 21 degrees. Now, our interest is to test whether this is equal to the value of P that we are given there, which is 0.47. So in the process, we are going to make P the subject of formula. So when we do so, we are going to transpose the product that we have next to P. So it will be 6 sine 21 degrees minus 0.3 times 6 cos 21 degrees. I'll need my calculator for this calculation. So I need to start with, let's see, that's 6 sine 21. So I'm going to say 6 sine 21. Then I want to subtract the coefficient of friction, which we have there 0.3 times 6 cos 21. So it's 0.3 times 6 cos 21. Let's check what we get. They are saying 0.4697, but to three significant figures, it means we are going to round using the fourth figure. So the first significant is 4, then 6, 9, so we'll use 7 to round, which will add a 1 to 9, gives us a 10, which will ultimately update the 6 to a 7. So it means the least possible value of P is going to be 0.47 to 2 SF. So it looks like we're correct. So when we are going for the greatest possible value, I mean, the pattern becomes easy, because we are simply saying if we want the greatest possible, this frictional force, it has to just transpose or cross over to the other side. So end up having P equal to 6 sine 21 degrees plus, last time we are subtracting friction, this time around we are combining because we want P to be greatest. So 0.3 times 6 cos 21 degrees. Now when I bring my calculator, we are simply saying we want to change where we have a negative there. So it's going to be 6 sine 21 plus, this time around 0.3 times 6 cos 21, which will take us to 3.83. So this time around, our P is equal to 3.83. So P is equal to 3.83 newtons to three significant figures. So there we are, we're done with the problem. It's another object on an inclined plane, and this one is a simpler one as compared to the first one where we have the pulling force also inclined at a certain angle. I hope you guys will find this interesting. Thank you, bye.